So now that we've had mathematical models that we can use to describe flow with friction and heat addition, we are now in a position to say, let's take a step back and think about how we get this heat addition, which we have now analyzed mathematically. In other words, we need to have some way of quantifying how much fuel is added, how much heat will be released if that fuel is burnt, and some concepts related to numbers like what is the ratio of fuel to air and how much heat will that produce. So in this unit, we'll look at purely quantifying the amount of heat added to the flow in terms of what fuel is used and how much of it is mixed with the air, and we'll assume that we are able to mix and burn it without going into the details of the mixing process. So let's get started. So as we know, in this section of the course, which is scramjet combustors, we've been meaning to look at the combustion process inside of the engine, and we looked at two main phenomena, friction and heat addition. And moving on from there, we said let's look at stoichiometry and try to understand how to quantify the fuel burning inside the engine and talk about things like equivalence ratio and heat addition, etc. But before we get there, since I'm a combustion engineer, I feel I should show you a small little flame on a much smaller combustor. This experiment here is a microcombustor, which has two parallel plates made of graphite, as you can see here, and we control the fuel air mixture into this burner by these methane mass flow controllers and airflow controller. To get this experiment started, what we usually do is heat the outside wall of this graphite plate using a blowtorch, and I'm going to show you that in just a second. Alright, so to get this experiment started, what we usually do is use this blowtorch to be heating the wafers. Let's talk about the blowtorch for a second. This blowtorch is burning butane as fuel and releasing heat in this flame, as we can see. And when I bring this flame close to the wall, it ends up transferring that heat to the plate of this burner. And eventually, when we light this experiment, a flame forms on the top and gets into the burner, which I'll show you in a second. But just conceive in your mind that if you have a flame inside this burner, that's going to be heating up the burner. And exactly the same thing happens inside the scramjet combustor. The two photographs here show the same burner I was trying to heat externally using a small torch. The photo on the left shows a pre-mixed laminar flame stabilized on the burner exit, and the one on the right shows the flame within the narrow channel formed by the two parallel plates. In the second case, the flame is heating the plates from within. We know from our daily experiences with cooking that flames are hot, but where does this heat come from? What causes the chemical reaction of a hydrocarbon fuel reacting with oxygen in the air to release heat? This sketch depicts a molecule of methane, which is this here, reacting with two molecules of oxygen here and here to form carbon dioxide and water. This reaction is fully balanced as fuel is fully converted to products. As can be seen, these molecules have chemical bonds right here and here between the different atoms. For example, methane has 4 carbon-hydrogen bonds and oxygen has 1 oxygen-oxygen bond. Let us take a closer look at the oxygen molecule. It is easy to understand that the chemical bond between the two molecules, as shown here, stores a certain amount of energy. Here's a cartoon sketch which just shows that the two molecules might be vibrating and there's some amount of energy stored in this bond. Similarly, the fuel, methane in this case, stores energy in the carbon-hydrogen bonds. When the reaction proceeds and the products are formed, the energy in the chemical bonds of the reactants, that is methane and oxygen, is released, and some of it is reabsorbed to form the new bonds in the product molecules. The difference in energy gets released as heat. So that we can now define heat of combustion as the amount of heat released per unit fuel that is fully consumed by the combustion reaction. Essentially, this is just the difference between the chemical bond energies of the reactants and products. More specifically, In engineering applications of combustion, we use the lower heating value of the fuel. In calculating this, the assumption is that the water molecules that are formed as product exist as water vapor, which will soak up some of the heat released during combustion, as opposed to a hypothetical calculation called the higher heating value that assumes that the water molecules are formed in the liquid state, which is very difficult to realize during an actual combustion process. Therefore, we will always use lower heating value LHV when it comes to applying the fuel heating value in our calculations. Typically, lower heating value LHV is tabulated for different fuels and will be provided for engineering calculations of engine performance. The title of this unit is Stoichiometry. Therefore, let us understand what this means. As we just saw, two oxygen molecules fully consume the one methane molecule in the combustion reaction. When reactions proceed in stoichiometric proportions, as in the earlier example, the reactants, in our case the fuel, is fully consumed. Using this concept, we can attempt to define stoichiometric ratios of air to fuel in our engine. By mass, this ratio is exactly how many kilograms of air is required to fully consume 1 kilogram of fuel. For 1 kilogram of methane, for example, let's say we'll need m kilograms of air to fully react it away. Then m is the stoichiometric air-fuel ratio for methane air combustion. Similarly, the stoichiometric molar ratio of fuel-air combustion can be defined as the number of moles of air required to consume fully 1 mole of fuel. Again, if 1 mole of methane requires n moles of air to fully react it away, then n is the stoichiometric molar ratio of methane air combustion. In order to determine what this m or n is going to be, we need to balance the chemical reaction. Let us start by examining a mole of air. From our understanding of the composition of the Earth's atmosphere, we know that typically we have 21% oxygen and 79% nitrogen. Therefore, we'll likely have 0.21 moles of O2 and 0.79 moles of N2 in 1 mole of air. Dividing this equation by 0.21 gives us the number of moles of air required so that we have 1 mole of oxygen. This number is 4.76. With this knowledge in place, let us attempt to balance the combustion reaction of some arbitrary hydrocarbon fuel CXHY burning in air. Let us say we need A moles of oxygen to balance the reaction, that is, to fully consume all of the fuel. Let us write out the balanced equation now. Looking at this balanced equation, it's easy to see that all atoms such as carbon, hydrogen and nitrogen are currently completely balanced between the left hand side and the right hand side. In order to balance the O atom on both sides, the value of A needs to be x plus y over 4. I will let you work this out as an exercise to prove it to yourself that if you set A equals x plus y by 4, then indeed the number of oxygen atoms on the left equals the number of oxygen atoms on the right. Therefore, the stoichiometric air-fuel molar ratio is 4.76 times A, since 4.76 moles of air are required to get 1 mole of oxygen, and we need A moles of oxygen to balance this reaction. Similarly, the stoichiometric air-fuel mass ratio is simply n times molecular weight of air divided by molecular weight of fuel. This is because the ratio of molecular weights allows us to convert from molar to mass ratio. Let me also point out that these expressions can be used to evaluate hydrogen as a fuel by simply setting x equals 0 and y equals 2. Now that we've understood how to calculate stoichiometric proportion of fuel to air for hydrogen and other hydrocarbon fuels, let us introduce the concept of equivalence ratio, which allows us to put different fuels that may have very different air-to-fuel ratios on a common platform. The equivalence ratio is defined as the stoichiometric air-fuel ratio divided by the air-fuel ratio currently present. If phi equals 1, then we have air-fuel ratio at stoichiometric proportions. If phi is less than 1, then we have a fuel lean mixture where amount of oxygen is in excess of that required to consume all of the fuel. Similarly, if phi is greater than 1, then the mixture is fuel rich with not enough oxygen to fully consume all of the fuel. Another important point is that when it comes to equivalence ratio, we don't need to specify whether we are comparing air-fuel ratio to that at stoichiometry on a molar or mass basis. Let us see why. We'll start with phi being defined on a molar basis as n of stoichiometric divided by n, where n is the molar air-fuel ratio. If we multiply and divide the numerator and the denominator by the molecular weight of air by molecular weight of fuel, this transforms it to m of stoichiometric by m, which are the mass-based air-fuel ratios. Therefore, equivalence ratio will be the same whether we think of it in molar or mass basis. Let's next proceed to the most important aspect of all of this knowledge of stoichiometry that we have just learned: heat release. If we have information on equivalence ratio and type of fuel, can we predict the heat release? To do this, we first need to figure out how much mass of fuel is put into the engine. To start, let's rearrange the equivalence ratio expression as m equals m stoichiometric over phi to obtain the actual air-fuel ratio. Next, dividing the total mass flow rate of air, which is m dot, by this actual air-fuel ratio m gives us the mass flow rate of the fuel. If we multiply the mass flow rate of the fuel by the lower heating value LHV, we get the total potential heat released. The last part of calculating heat release is realizing that engines may not be 100% efficient in burning all of the fuel, owing to design trade-offs, as we saw in the case of flow with friction and heat addition. Therefore, the actual heat release will be a product of the combustion efficiency and the total potential heat release that we just calculated up here.